Okay. Yeah, it's time for class to actually start. Okay. Well, really, the agenda for today kind of depends on y'all, because to take on homework issues.
I've made some progress, which is good.
Okay.
My question is for number two.
Yeah.
The first part of number two. How can we test our code to see if it works?
Okay.
I don't even know where to begin to test it.
Okay.
Is there an example that I could use to test it? Does that make sense?
Well, that's why we have a very, very first part is computing the exact solution.
Wait, what? Was it that easy?
No.
You mean number one? No.
Number two.
But I thought the whole point of that beginning part was to approximate.
Well, no, we're going to have the exact solution so we can compare the numerical solution to it. And when I showed you when Jessica had the exact solution going, but turned out to have too few points. So then I showed you all. Here's what it looks like. So then you can plot that and your computed solution and make sure they match up. Okay. That was a very interesting look of uncertainty.
Yeah, well, I felt like I should have known what you were talking about.
Oh, okay. It'll come. Okay. Do you have your formula for the exact solution yet?
I cannot get it to the
I have the code that will approximate UXX.
Right, like your matrix. Okay.
Yes.
Okay.
Like in solving the system, U equals A / F, right?
Yeah.
That's going to give me my approximation.
Yep.
I've created A, and I have a for loop that will create that does the right hand side. So it creates a column vector of X values.
Yeah.
To create F, a column vector of F.
Okay, so you have F.
I have F and I have A.
And therefore you have U.
Exactly. So that's where I'm at. But I don't know if it works or if it's right.
Okay.
And I don't know how to test it.
Okay. Well, first, what does U look like from plotting it?
Oh, I haven't plotted it.
Plot it.
Plot it?
Yeah.
Okay, so if I've solved for you, then I need to plot it? Okay.
Yeah.
My question's on that same one. I got it to where it had slope looked like roughly 2, and then you said to do fourth order accuracy with the stencils, and that's kind of where I'm stuck, because your hint said to do a 5-point stencil for the interior rows, but a 6-point one-sided stencil for other rows.
Oh, wait a minute.
And that was kind of confused about that.
6. Wait a minute. Okay, so 3. I think I just had Carly do the wrong thing then. Yeah. Okay.
So anyway, that's the part I'm stuck on.
That was quite a transplanting operation there. Okay. But now the room's more balanced, so that's good. Okay.
No, there were 3 people on that side.
Well, yeah, it was kind of a staggered grid. It'd be perfect if Carly was here, but okay. So, all right, have you plotted it?
Well, now I am looking. I don't think I have all my inputs correct. So like, hold on. Give me a few moments. I need to look.
Okay.
But like, what should my F be? Because I'm gonna have to put in F.
What's your what? Your
My F.
yeah, so that's a given f.
Negative UXX.
No.
F equals negative UXX.
F.
Oh. Oh. Okay.
Oh, you didn't have it in there yet?
Correct.
Okay. All right, go do that.
So my only input should be in, like the number of. No.
Okay. Hold on. Material 6 months. Okay. And okay. All right. So while she's doing that, okay, the fourth order bit.
Yeah.
Okay.
Sorry.
So, so what point are you at in that? Or
Well, I know you sent. It says to use stencils can be used, diff rule and helper and make Lagrange, which I think you sent us diff rule, but not. You said go look for the other. Anyway, the stencil part, I was not.
Okay. Let me
familiar with
check
that.
here as to.
Versions. So like.
Okay, so I sent
QB
so I sent
hits.
you diff rule. Let me take a look at that real quick. Oh well, okay. This diff rule that I sent you
Yeah.
doesn't require anything else. Like it doesn't need. Yeah. What I mentioned in the handout has a helper function make Lagrange, but this diff rule I sent doesn't require it. So what you can do is. Okay. So for a 6-point rule for uxx, the second derivative. Okay. Using x naught plus IH, where I goes from all the way from 0 to 5, so 6-point rule. Okay, so the way you would call diff rule to get the coefficients is, okay, so 0 to 5 indicating which multiples of h you want. And because it's for second derivative, we fill in 2 for the second argument. And that'll just give you a column vector of all the coefficients in order. So the coefficient of u of x naught, and then u of x naught plus h, and so on. So those,
So it would be plus 2h and plus 3h.
yeah,
Okay.
yeah, and so then that's what you would fill in the first row of your matrix. And then similar for the last row, but you want to use x naught minus h minus 2h. So you want to go from minus 5 to 0. And you put that at the end of your last row.
Okay. But then the middle's different. It's just gonna
Okay, so the middle, that's right, you don't have those coefficients either.
be.
All right, so this is row 1. The interior, all right, so that's going to be a, okay, let's see.
5 point.
Yeah, 5 points, and okay, the boundary conditions are not an issue away from the boundary. So you're going to be using minus 2h, minus h, 0, h,
Plus
and
H
2h.
plus 2H.
Yeah, so minus 2 to 2. For that centered 5-point rule. So, in general, the order of accuracy of any of these rules is equal to the number of points that are used minus the order of derivative. Most times. So in this case, we want second derivative. We also want fourth order accuracy. So that's why we generally need 6 points. The only exception is if it's centered, where the symmetry gets you extra degree of accuracy. So that's why we need 6 points on the boundary, but we only need 5 in the interior.
So once we get those row of coefficients, that makes our matrix.
Yes.
The new matrix A?
Yeah.
Okay.
Yeah, we're using a whole other matrix because we want the higher order accuracy.
So basically, we use diff rule to build our coefficient, take that coefficient, and then build the matrix.
Yeah. So that, because for the previous one, we already knew what coefficients we needed. It was at 1 minus 2, 1. For a second order center difference, now we just need to generate the coefficients for,
To get
yeah.
And then compare it the same way, right, like plot it to do the comparison,
Um,
and then
Yeah, so in that case, so for this part, you're going to be plotting versus your error versus h to the 4th and making sure they're parallel. Now here's a really strange part. Carly's already done this, but I hadn't caught it. She'd actually used a 5-point stencil for all rows, interior and boundary. So use diff rule with not enough points. And that would be a third order approximation at the boundaries.
So to get fourth order, though, we have to use the 6 point.
Yeah. I mean, well, fourth order accuracy, generally you got to use fourth order approximations every row. So she had fourth order in the interior, so that she had that. But at the boundary, she had like 0 to 4.
She's still using a 5 point.
5 point, and that would mean third order accurate at the boundary. But here's the strange part: the order accuracy of her overall approximation turned out to be better than fourth order. It happens, but chances are generally it would not. But yeah, I had to go to tell her to fix that. Yeah, so then you use that matrix with the same f, and then plot the error.
And just the last row we do opposite order though. Correct?
Yeah, so it's still going to be left to right in terms of a number of points. So because here you have points only to the left of x naught.
So it's going to be like that goes outside of it, kind of.
Well, like, whereas here you listed x naught plus h, and so on. Here you'd start at minus 5h, minus 4h.
Oh,
Yeah. So you have to specify that order when you call diff rule, and you'll put them in the last 6 spots of the last row. Sarah, how are you coming?
I have to look at my A and my F, the matrix dimension. Like I'm getting an error saying that dimensions like don't agree.
Oh,
So I'm trying
okay.
to figure out what I did.
Okay.
Oh wait. I think I made a row vector instead of column vector.
Oh, okay.
That would do.
Yep.
I copied that diff rule that it gave me into the command window, and it gives me an error function.
Oh, don't put copy in the command window.
Okay.
So you need to save a file, the M file, with your other files,
Mm-hmm.
and then
Maybe.
call it from the prompt.
Oh.
Now, when I say sparse, when I make A sparse, basically wherever there aren't values in A, because it just has the diagonals, it fills in zeros, right? That's what sparse does.
Yeah. Well. You're not
I'm just
using.
trying to make sure that my A is the right dimension. Like,
Right. Are you not using SP diags, or how are you creating a matrix?
oh, well maybe.
And you don't have to use SP diags, but
Yeah, I mean, I used a full,
you like, use like diag to make it full, and then you call it sparse on it.
right?
Well, that works. So yeah. So you've already made a matrix that has mostly 0 entries.
Right.
All sparse does is just represent it differently by not explicitly storing the 0 entries.
Oh, okay. The matrix should be in by.
And by n.
By
Okay. Yeah, I guess it's your turn now. Okay, so this is this. Okay. All right. So here's your x. Oh, here it should be derivative of phi because it's phi x.
What was it? Oh, it was. Okay. So other than that, though.
Well, I need to move the rest of it. Okay, so I spin f will be fine. A is okay. So those are right diagonals, and then is okay. It looks good. Yeah. So what's fix that. And-
Then what?
Oh.
What's my next step?
Okay. All right. Well, what do you do first? Go ahead and fix that and run it because you're already going to plot a solution. So we can at least make sure that's right, and then I'll fill you in on the next thing.
So,
Yeah.
Would row one and the first row and the last row just be like the inverse on the reverse?
Yes, it
slope?
will be. Yeah.
Okay, because that's what it's.
Yeah. There's a symmetry variable coefficients.
Okay.
Did you say you fix that?
Okay. Yeah. Go ahead and run it.
Is that a good number?
More.
What are we on?
8.
28?
I'll memorize your powers too later. Okay. That looks good though.
Okay.
Okay, so now somewhere I know we talked about. Oh, you do have a formula for solution.
Yeah.
Good. Okay, so now let's go back and so make a number vector that represents your exact solution, and you already have your x vector, so you can just make that vector to be your exact.
So this is where this is coming
Yeah, we're about to get to that. But yeah, you see the exact solution there to compare against.
in? So this would be like
Yes, it is you had.
okay.
Yeah, you need a dot there for a vector. Okay. All right. Well, how about this? After your plot statement, do a hold on, and then hold on to it. And then plot that in a different color, and then we can eyeball it and make sure they probably do, but this will really tell us. Okay, yeah, they match. Okay, so now for the error analysis part. Okay. All right. So what you'll do now is, so here you're picking out a particular n and computing a solution. So now you need to do this for a few different values of n. And what you need to store from all these solution attempts, you do it in loops, like in your research code, where, well, in that one you're doing different time steps, but here you're doing different values of n. And what you'll store are a vector of h's and then a vector of errors. And then you log them against each other, and also log of h squared, and they should be parallel. Okay.
So xj is j times h, where h is 1 over n plus 1. But then you plug xj into n to create.
But you have vector of x values, right? Or do you?
So, but xj is j times h.
Right. So that'd be like.
So in a one for loop, I just have one for loop. It's
Okay.
like f for j equals 1 to n, xj equals j
formula.
function with X and J.
Okay, that's fine.
And
So
so I
you,
don't need the X, I don't need a vector X values,
well, I
because I
guess-
just do it in that
do-
for loop.
well, it'd be a good idea to have the.
Well, I stored it after, like I
Okay,
stored,
yeah, all right.
but I don't really need it for multiplying. Like I don't,
No,
I store it because I
yeah.
can.
yeah.
And then after the for loop,
Then you have your F vector.
I have my F vector.
Okay. All right. Okay, so now you have your F vector. You have your.
And is it to create the F vector? I just have F after the for loop. Should it be in? No, it shouldn't be in the for loop.
Well,
F
you're filling
equals-
it in.
Filling it in. Is that it? Should it be inside the for loop?
Oh, well, that you don't need.
This?
Yeah, I'm not sure what that's for.
I thought this is what.
Okay, so. Oh, but the way this loop is filling in, when you have xj and fj when they're not pre-allocated, now that will treat them as row vectors, and you really want them to be column.
Right. That's why I thought
Oh, but that won't do that.
that would do that.
You take transpose, like using a single quote. That will transpose.
So F equals.
Okay, and you have your
And
A.
I'll just go ahead and do.
Yeah, we can update it. Now, exactly, then you can plot U against X. Or, I don't know, I'll worry about it. Okay, so now, okay, let's give this a whirl. Oh, something's wrong. And there are oscillations, but yeah, definitely the solution should not be that big. So, okay.
I'll make sure.
So you have more. Oh, do regular slash.
Oh my. Yeah.
Okay.
Let me make sure that was
Oh wait, there's one more thing. With your F, the formula has a sign of 1 times derivative squared.
Oh, okay, okay.
That part's fine, but
Oh, wait, why
After that.
is this?
because you're at 18 pi x, yeah, that's pi x, but that has to be squared. Okay, and then
And
I'm
let
not
me
sure where
make
that 32
sure-
is coming from.
Yeah. Oh, because this is just X.
Okay, that's good to go. Alright, that looks good.
How do I know that looks good? Like how would?
Well, do you have a formula for the exact solution worked out? That's what I was talking some time ago about undoing the product rule.
Undo product rule?
Yeah. Oh, you haven't done it yet?
No.
Okay.
Alright.
Okay.
So then I would just plot that.
Yeah, I mean, you'll see they match up. But it will. Okay, how's this side of the room doing?
I have the coefficients, so I'm just to
Okay.
reinvent A. I'm just looking at what I had previously. But I have the 1/8 squared component.
Yeah, that's still gonna be
That'll
there.
still be there.
Yeah.
So the whole SP diags is out of the picture for that.
Well, what I would suggest is go ahead and do the SP diags using the interior stencil coefficients, because those will fill almost every row. And then just alter the first and last rows.
Like you just manually alter
Yeah.
the first and last. So you use diags for everything interior.
Yeah.
Okay.
Yeah, because then you'll just be filling in those entries, and that'll overwrite what was already there.
Okay. So where before, like I had it designated, 2s and -1s designated, I'm just gonna use now my 5-point coefficients that I have.
Yeah, so you'll
but just
five
the 5
diagonals.
of them, and then
Yeah.
just run them through SP diags, and then just,
Yeah.
okay.
And now your diagonals will be instead of just
All, yeah.
those 5.
Mm-hmm.
Yep.
Okay. Let me see if there's anything else on the next part I can ask a question about. So that I can
Okay. Oh, all right. So the next part is where you go back to the A
Backslash.
from a previous part. Well, all these parts use backslash.
Right.
Are you talking about part C?
Yeah, but
Okay.
go ahead and finish saying what you were going to say.
Oh, okay. So yeah, part C, because whereas in part B you change the matrix, use the same
Can
F.
change matrix.
Now
same
it's the
process.
opposite. So now
part C go back to the original A
yes,
and then change
change the F.
F. Okay.
Yeah, and
Make a note of
so and it's telling you to add h squared over 12
that. To the right, yeah.
d squared f. Now your matrix is the same as minus d squared. So you can just multiply that by your f vector. The only part that has to be the only complication with that is f is not 0 at the boundaries. And I mentioned in class how you had to tack on this vector that includes the values of f at 0 and at 1. I think I gave you a formula for that. It'll be in your
I
notes.
think I remember you talking about
Yeah.
it in class. I'll just have to go back to the
Yeah, so once you add that on, you'll have your correct f. And then you can verify fourth order accuracy just like in part B.
So on the diagonal values, it'll be -2, -1, 0, 1, and 2. Is that how? Because of the main diagonal
yes,
is
it will.
0, so I would go the first coefficient would be -2.
Yeah.
-1, 0, 1, 2.
Well, yeah, and you're specifying the diagonals.
Yes,
Yes.
for the
That.
diagonal specific. Yeah. So like the main middle diagonal is 0, always 0.
Yes.
Okay.
Yeah. So this will be pentadiagonal.
Okay. What's the best method once I do get the diagonal worked out to manually add it in?
Okay. So
Just so that it doesn't, because it's going to shift.
So you do something like this. This is the first row. You have A, row 1,
Mm-hmm.
comma, and you want to fill in the first 6 entries.
Right.
So it'd be 1, 6 equals, and then it'd be a row vector of those coefficients.
What they were, yeah.
Yeah.
Okay.
Now keep in mind, diff rule returns a column vector, or if you just be copying those coefficients manually, but make them a row vector.
Just transpose it.
Yeah.
Yeah. Okay.
Okay. And I know I mentioned this earlier. Talking about that boundary
Yeah, well, I
thing.
mean, that's just that first part. So once I have to mesh it all together, though, right? So I'll manually label that first row. So I just name the middle part, like 2 through whatever you know what I'm saying?
I'm not sure. Okay. Well, all right. So that'll only take care of the first row. You'll have already done the other rows.
Right.
Do your SP diags first.
Okay.
Then do this, and similar.
And for the last.
Yeah. Oh, and then multiply by 1 over h squared. Do that at the very end.
Do that last.
Yeah.
Okay.
I just wrote in class some time ago, but that was quite a while ago, so I'm just repeating it here so everybody has it.
Is that F sub 1 at the bottom?
Yeah, f of 1. Yeah, so the boundary values to complete the center difference, since f is non-zero on the boundary. Oh, or did we make that plus? Sorry, it's plus.
Yeah, that's probably all I'll be able to ask until I like get those next two things done.
Oh, yeah. What?
Some more sound and air sound.
Well, since I'm here we're all here for 15 more minutes. So,
That's it.
our usual time, yeah.
Wow.
uh, so any other tidbits needed to make sure that things can move along?
Okay, so B and C. So for D, change the right hand side. So just completely change the f of x. So which A would be used for that one? The original A? Still use the
Wait, for
original?
part B or
D.
D?
D.
Oh,
Just so.
yeah. So here we're going back to second order.
Okay.
So
Original.
same A as the very first one, and then yeah, the F will change just to fit that F. But then you need to compute an exact solution for this case.
Oh yeah, we computed that.
Yeah. So what you'll do is you'll take that function and you'll integrate it twice, and take the minus of that. But when you integrate, you're going to get, well, you do it separately for each piece. And each time you integrate, you get a plus C. So you're going to have 4 plus C's altogether. And the whole thing has to satisfy the boundary conditions. So it's 2 conditions. And the 2 pieces have to match at x equals 1/2, wherever 2 pieces join. And the derivative does too. So that's how you get 4 conditions for 4 C's.
I mean, that's ambitious.
What?
I said, I mean, that's ambitious to do that part, but I figured I'd ask ahead of time just in case.
Okay, yeah, all right.
When I plot the exact solution of U, it also has to be a vector, doesn't it?
Yes.
I think that's what
Okay.
I feel like 2 is never ending.
Um,
2.
yeah,
It's
that's-
kicking my butt. I'm like, I'm still
Um,
on 1, 2.
Yeah, the love of the multi-parts isn't helping. And actually, yeah, once you get through problem 2, then problem 3 takes a whole lot less time. And actually, most of the other problems will also take less time.
Oh no,
Oh, what happened?
they're not the same. I think one of them.
Oh, really?
But I also think, I don't know if my use is right.
Okay.
Well, my check.
Numerical solutions are closer. Okay.
That's what it looks like. That's wrong.
Oh, okay.
Yeah, I think my U. So I
Oh,
changed
your
it.
square's in the wrong place.
Oh, wait. Okay.
Well, yeah, okay. It's just still needs a dot, though. Okay.
Oh. Is that really gonna fix
Okay.
it? Yay. Okay, very good. All right, now I can actually start the real part of the problem. Great.
Okay. Okay. that looks a little disconcerting. Jeez. What? Okay. Well, so what you can do? Okay, oh, yeah, the thing is, right now your function is only taking 1 value now. So, and there's one more way you can do this, but probably the easiest way in your case is make this function return as output, not just U, but also H and the error. Yeah, like that. Okay, and now
I forgot function.
what? Oh, okay. All right. Well, if you haven't done it, then okay. All right, and then so now what you can do is in a new file, in the script, you can call this function say 3 times, and then get like 3 H's, 3 errors. You can just make up the end values. And as long as you take these 2 outputs and store them in different elements of vectors, then you have what you need. So actually, you won't even need a loop after all. Wait. What do you mean?
Well, because at the end, I wanted it to output what the error was.
Oh, okay, all right, but that, so really, take the norm of that, that's a vector.
Right, and it's a log, a big vector.
Yeah.
I mean, this is the error though.
Well, technically, yeah, but we're really interested in its magnitude. Yeah, so it's that's what we'll actually plot.
Oh, you want the
Yeah. Actually, divide that. Divide that by the norm of u hat to make a relative error. Okay.
And U hat is my approximation.
Or
not
you
mine.
have to use the exact solution.
Well,
Wait, you did the other way. Okay, so
Yeah.
you put the u then.
okay, that's why I thought that's what it should be.
Okay. Yeah, so then if you try this for two different, like, whereas if you double the number of grid points, the error should go down by a factor of roughly 4.
Is it still supposed to be that? I mean, what's a vector?
Oh, wait. Are you still printing a whole solution? Need a semicolon somewhere?
It's this is what's printing.
Oh, that's just going to be a number. That's weird.
Yeah.
Wait, wait. Go back to go all the way bottom. We can do a CLC. Go ahead and run it again. Oh, that's the output from the function. Okay,
Oh,
Yeah,
okay.
when you call it,
yeah.
put a semicolon. You don't
Wait,
take
wait,
anything
you
there.
can't call it.
No, at the command, at the prompt. At block command tag up, put a semicolon there. Okay. Yeah, that's the error.
Oh,
That was 1024 points. Now do it again with 2048. Okay, and okay. Yeah, so the errors, the second order.
So I think I have the first row of that, but I tried to do the indexing of how to tell the nth row the last 6, but it doesn't want me to use anything negative to say that.
Well, what you can do is, since your last element would be the n element,
Mhm.
and then the 5 elements to the left of that. So
like that's my first row, and then that's my interior, and
yeah, so if you look at the last 6 elements, so the index of the last one would be n, then n minus 1 before that, n minus 2, etc. So the indices would be from n minus 5 up to n. Yeah, so it'll let you do that.